Hello everyone. I want to wish all my viewers the happiest of holidays and a happy new year. And of course, clear skies. As you may or may not have seen on my in my community section of my channel, I've been talking a little bit about my spectrograph that I've made. And today is the day that I get to show you some of my results. What I will do is bring up an image or two. This is the Solex. You would attach this to something like a 50 or a 60 millimeter guide scope in that range. And with the correct filters on the front of the scope, you would be able to get spectra from the sun. I have two grates. One is a 300, and then the other one is a 2400, which would be what you would use with the sun. And the 300, which I have in for this test, is mainly used because it covers a large portion of the from UV to IR spectrum. So in this format, I shot, it's pointing at the other sliding door with the curtain in front of it, that happens to be over here, and I will show you that spectrum. And then for this test, I mainly have it in this configuration, which I call, or I don't call it, but this is called the LabX setup. And this is 100% 3D printed. I used PETG with carbon fiber. And the reason why I went with PETG is mainly because it's a higher temperature filament, and the carbon fiber helps to dissipate some of the heat that would be generated by the sun if you were to take it out in the sun. I have just a little bit under one spool, so I use 1.75 millimeter filament, and I think it's like 1,000 meters, give or take, something like that. 1,000, I think that's what it is. And I used about 3/4 of a spool, and the spools cost me close to 50 bucks, mainly because of the carbon fiber. So I purchased this from Maglite, got it on sale for 10 bucks, and it is the tungsten version, not the LED version. LED light isn't something you want to show or to test with, because LED light has got a funky looking spectrum, where tungsten's got a nice broadband spectrum. The slit is in here. There's a lens here, the collimator lens. The grate is in here. Then there's another lens here. And I purchased this ZWO helical focuser. So my total investment minus the camera is a little under $800. Now, when I first, many moons ago, when I first had an inkling that I thought I might want to get into spectroscopy, they were going, the cheap ones were going for 5,000 bucks, and they were not very good. This thing, for $800, and I made it myself, is such a better deal, because you can just purchase any kind of grate you want, and it changes the resolution of the spectrograph. So from that standpoint, this is much more flexible than what I would have been able to purchase years ago. And I had the pleasure of making it myself. Now, the grate slit And optics came from a French company called Chiliac, I believe it is. Chiliac. And that was the most expensive item, was that stuff. I think it was like $650 US. Everything else was nominal, as I mentioned. And what I will get into now is showing you my remote desktop session that has SharpCap running with that camera that you saw in the pictures. And right now I do not have anything at all in front of the camera. So I will put my neon bulb in and I'll turn it on. And this is Neon Spectra, or the Spectra for neon. Now don't mind my hot pixels because I will fix that right now. And you will see that this is what I use to calibrate when I go into other software. So the next thing that I would do is turn on the tungsten light. Which is coming up now. And I need to lower this exposure a little bit. And now this is the broadband spectrum light. And you can see that this is UV on this end, and this is the IR on this end. Excuse me. And I would grab this because this is my base light. And let me grab a filter now. And with the filter, what I will be able to do is show you what happens to the light when you add a filter. So I'm going to stick in my NBZ UHS filter. And the reason why I want to stick this in, because it's pre-shifted. And this is what it gives me. And this is with the filter straight on. Now, because of the fact that this is for a fast scope, the light hits the filter at an angle. So as I rotate the filter, what you're going to see is the filter starts to shift to the right or the left. And that puts the bands in the sweet spot. And that is one of the reasons why you need, for fast scopes, anything below F4, we'll say, is you really want to have filters that are shifted for these faster scopes. So I thought I would show you that. I'll leave this here because when I get into actually showing the bands, the filters with a corrected band. So I will turn this off, we'll turn the camera off, we'll leave this, and now I'm going to start up RSpec. The software that they recommend to use with the LabX or the Solex or the StarX is free. But because there's kind of a French-English thing going on, I'm having a little trouble trying to figure out how to use it. So I had, years ago, I thought I wanted to get into spectroscopy, and I was looking at RSpec. And the reason I was looking at RSpec was because they have a package where you get the grate, and it gives you both the star, and then off to one side would be the spectra of that star. And then using this software, you can then calibrate and then figure out what the spectra of that star is. Now, it doesn't have to be just a star. You could be pointing it at a galaxy or a nebula, anything. Now, at the moment, what I want to do is open my tungsten light, and now I want to open my neon light, and the next thing I want to do is calculate, or not calculate, but calibrate the neon, and then once that's calibrated, then I can look at the spectra for all the other stuff that I shot today. So the first thing we're going to do is open up the calibration, make sure that's selected. I'm going to grab the highest peak, and I happen to know that that is 5852.5 roughly. And then I'm going to grab this peak, and I happen to know that that is 6717.0. And now I have, once I apply this, you can see that this has gone from pixels to angstroms. And I can close this, and if I select neon and I zoom in on this, we will see that the peaks now line up with the neon peaks, or the neon lines. And that's what you want. Now, I could add more points, which will enforce the calibration a little better, but for what I'm doing here, this is plenty good enough. So I'm going to turn this off. I'm going to go back to my tungsten, and I will turn on the hydrogen Balmer lines, and this is HA and this is H beta. And if I zoom in, you can see I'm on one of those peaks. And I'm in not quite one of those peaks. But again, this is different type of light, and it's just a base. And because I'm using a color camera, I have 2 green pixels, so the green is a little heavier than what you would see if you had a mono camera. This curve would be more flat. What I want to do now is load up one of these filters. So I'm going to use the IDAS MBZ UHS, and you can see the shift. So if this was not a high-speed filter, these bands would be in this range. Same with this one. So what I can do is I still have this filter. Now this is not going to be the best test in the world. I can't do that. Ignore that. I was going to show you this shift, but I can't because this is not a live shot. But that's okay. I could show you the other stuff that I did. Now, with my Raza 11, it has a very steep light cone, and that steep light cone would move these bands into the regions of interest. So let's look at the GNB, and the GNB is a filter from IDAS for galaxies and nebulas. And the next one I want to look at is this one, the Omega D GM-NPB nebula filter, and you will see that they're very close, but this one goes out into the IR regions a little more. So if I go back to the GNB, you can see that they're close, but we're getting more of a little bit of everything more on this end. Let's look at the L enhance. Looks good. Then the L extreme. Oops. Now I don't have the L extremes chart, and so I would have to find out if this is in band or not. I can't remember what the L extreme was really trying to get. Oops, did it again, Jeff. Here's the L Pro. And I did it again. Here is the Sky Glow. They're very close, but the Sky Glow is again going out further into the IR than the L Pro. Then we have the Triad. So there's a line for the H alpha and the H beta, and I think this is sulfur. And I'm not sure what this is. It's either sulfur or O3 or O2. Excuse me for not knowing my elements. And then this is the Celestron light pollution filter. So you can see that the peaks are much lower with the Celestron filter, and they're much wider. And where I get into trouble is when we start getting into these blues. That's where I think I'm getting hurt with light pollution. 2 years ago, the state mandated LED streetlights, and when I started up for the season 2 years ago, a lot of my filters were no longer working as expected, and I was getting a lot of wash across the whole image, and it turns out that that's from the LED streetlights. So if you're finding that for some reason filters that you thought were working the next season aren't, I'll guarantee you probably got LED street lit, and it is destroying our ability to use our existing filters, and it is destroying our ability to see the night sky. And that was one of the reasons I wanted to get this or build this, was that in the Solex mode, without the scope on it, all I have to do is point it up at the sky, and and grab the spectra. And that will tell me what my night sky light pollution is with the spectrum. And then I can compare that spectrum to my filters. And then pick the best filter that will fight that my specific light pollution. So as you can see, a lot of things have changed in the hobby. It is, when I first got into this hobby 50 years ago, there were no cameras, there were no go-to scopes. I mean, it was I had a huge C14 on a big clock drive, and there was no deck. The deck only moved like 4 or 5 degrees, and you had a push button box. You had 4 push buttons. And to guide, you manually guided with that 4 button box. And then when cameras came around, it was like a whole new world. My first camera was a DSLR, Canon 5D Mark III. In fact, I HA converted that, and it still makes pretty pictures today. And then I went saw an ad for Mellencams, and I've been using Mellencams. I have a DS62, which I believe is the 455, the 62 megapixel camera, and then I have a DS24, which would be the IMX 410, I think it is. I also have QHY 268, a Mellencam DS 2.3, and some other cameras that really are a little too old for today's technology. And using 3D printers, if you are into 3D printers, the 3D printers and astronomy are like kissing cousins. They were made for each other. And this little project of mine is living proof that with a 3D printer you can make some really exciting instruments that work very, very well, I must say. Now, I will never be able to do nor do I want to do what Jim Thompson does. That's not why I got this, and I really don't want to go after star spectrum per se. I could, but I would have to upgrade the unit to actually guide, because you have to guide on the slit, and the slit's very small. I don't know if I want to go that route, but I could do solar. Solar would be cool. And again, like I originally, my whole reason for doing this was to figure out where my light pollution is, and to try and match filters to my light pollution. So I want to wish again everyone a happy holiday of their choice, and a happy New Year, clear skies, everyone. If you have any questions, you know where to comment. Thanks.